I use my logic analyzer to explore, debug, develop and reverse engineer all kinds of things. Almost 10 years ago I bought my Aliexpress Pro 8 and it has been a rock solid tool ever since. The downside is its price. At around $1,000 it's far from being cheap. But recently something new has popped up in my feeds. On paper this logic analyzer looks comparable to the Aliexpress, and in some areas it even claims to outperform it. And it's only $69. Too good to be true, or did we just find a hidden gem? My name's Robin, welcome to the shop. Let's take a look. The first metric that comes to my mind when thinking about logic analyzers is the sampling rate. On paper, the SLogic 16U3 promises a whopping 800 megasamples per second when using no more than 4 channels. The Logic Pro 8 maxes out at only 500, which is not an insignificant difference. Anyways, let's jump in. I've set up my signal generator for a 5 MHz square wave. Technically it can go up to 24 MHz, but things look like a sine wave then instead. I mean, the generator is designed for a 50 ohm load and my logic analyzer and scope are sort of in the mega ohm region. I don't have any proper 50 ohm termination on hand and we're kinda leaving my comfort zone here anyways. Now let's look at a typical workflow. With the Aliexpress hooked up to our signal, we can jump straight into its desktop software called Logic. It automatically detects our device and we're ready to go. So let's see, at 10 megasamples per second, which is the theoretical minimum, we're starting to get some data and even a 5 MHz frequency readout. But there's something interesting going on. It seems like every now and then we do not get a good capture. There's a gap. Here's what I think. The signal generator and logic analyzer are slowly moving out of phase. And at some point we're starting to sample exactly at the transitions. Then a bunch of readings will just be undefined garbage. We need 20 megasamples or more to start getting good readouts. And we're just looking at a stable clock. Chances are high we're still missing timing problems or glitches on a bus. So giving those $5 24 MHz logic analyzers a quick look reveals that we're pretty much already leaving their comfort zone. I still think those are amazing if you are tinkering around with UART or other buses with a low baud rate, but anything above that is pretty much impossible. Let's hook up our S16U3. As the name suggests, it has 16 channels, which is nice, but actually I rarely ever need more than 4 channels simultaneously. The Aliexpress, or Aliexpress I guess, has individual leads for all the channels and ground connections. Here we have a single coax per channel that exposes the signal and ground connections at the end. While this is probably better for signal integrity, it can be tricky to connect your subject as the leads at the end are short, but I mean I could always use the ground from a different channel if this ever gets in my way. Speaking of connections, I don't like the clamps that came with this. The connection pin is kinda where your thumb is supposed to go. The Aliexpress clamps expose them at the sides, which is not only a lot more convenient but also allows you to daisy chain the signal or use them as a female to male adapter. Also, the cheap clamps just fall apart all the time. I definitely buy a pack of spare clamps with this logic analyzer. Honestly, probably just get the Aliexpress spare clamps, I guess. So let's look at PulseView, the software of choice for this analyzer. Well, actually it's SIGROC. And SIGROC is a really nice project. It's a general purpose library to interface with lab equipment. It can, for example, also talk to oscilloscopes, multimeters and other stuff, which makes it really nice for automated testing. Just think about getting one of those Cypress FX2, which is kinda driving the 24 MHz $5 cheap logic analyzers, and putting it on your PCB test rig. You could then have SIGROC with a Python script running your entire test setup. That'd be pretty sweet. So let's jump into PulseView and take a few measurements. At 10 megasamples per second we're getting a good frequency readout with the same gaps from time to time. At 20 to 25 megasamples per second we're having a good enough capture to work with, which is pretty much what we expected. Now what I like about PulseView is that it adds those little dots per capture. This gives a nice indication about how many captures you have per clock cycle, which is quite a lot at 800 megasamples per second. Side note, we're now having 16 cables tangling around our workbench with no way to tell which corresponds to what channel, other than tracing it back to the connector. I mean, yes, we can unplug 8 channels, and that's what I did, but with the SAILI all the wires are color-coded to match the channel colors in the software. So I'd probably buy a set of colored heat-shrinking tubing, at least for the common channels 1 to 4 or 1 to 8, that matches the colors of the channels in PulseView. Alright, so let's move to a fun little project so we can see how the protocol decoders in PulseView work. I salvaged this LiDAR unit from an old vacuum robot, and it would be nice if we could read its measurements. It only has 3 wires going to it, which are labeled VCC, GND and TX. I would suspect TX just being UART, but let's take a look. With UART I always play around with the decoder settings until I don't get any framing errors anymore. Here it seemed pretty easy. A baud rate of 115/200 with a standard 8/1 settings seemed to make sense. Those chunks all seem to share the same starting bytes, which may be some frame header or so. So I did what we would all do nowadays and just exported my capture and dumped it into ChatGPT. And sure enough, after thinking for a few minutes, it actually figured things out. It gave me a surprisingly solid explanation of the frame structure, angles and distances, the whole thing. Like, how cool is that? Next, I asked it to write a custom protocol decoder, and it kind of did it, in theory. In practice, I just couldn't get it to work in PulseView. Well, out of curiosity, I tried the same thing with Logic, and this time it worked immediately. A fully functioning decoder showing the angle and distance of every single measurement point. That alone saved an enormous amount of time. Honestly, that part was already pretty mind-blowing. But I wasn't quite done playing with this LiDAR module yet. What if we turned this raw data into a proper desktop radar display? So I spun up a new UV project, opened the GitHub Copilot agent and went back to ChatGPT to ask for a clean protocol summary I could drop into GitHub Copilot for my Python project. And at that point we're already wiped decoding, so why not let it build the entire GUI as well? Inside VS Code I gave Copilot a protocol summary and told it to build a Python GUI that visualizes incoming data as a radar screen. And it just worked, instantly. I could clearly see my hand moving towards the LiDAR sensor in real time. After asking it to add a centimeter scale and a zoom slider, I could even verify the distance measurements were correct. Now that was the moment where it really hit me. Isn't that incredible? Alright, back to the logic analyzers themselves. Both handled this task without breaking a sweat, which is exactly what you'd expect. I mean, it's a fairly slow UART signal, right? But there are a few annoyances. The included USB cable is way too short, and while PulseView is powerful, Logic simply feels more polished overall. Adding custom decoders and looking at analyzer data feels a lot better there, but that may just be a skill issue. I'm not affiliated with them or SAILI at all. I bought both devices with my own money. But at $69, this logic analyzer is a really solid purchase in my mind. The clamps aren't great, the cable is too short, and PulseView isn't my favorite UI. But most of that is an easy fix, and the core functionality is absolutely there. For most real-world use cases I can think of, it does exactly what you need it to do, and it does it well. So is it actually better than the SAILI? The honest answer is, it depends. The SAILI can also be used to sample analog signals, even though that's a bit limited at about 50 megasamples per second at a 5 MHz bandwidth. Still, that's a capability the SLogic simply doesn't have. On top of that, the SAILI is built to tolerate much higher input voltages. Each channel is protected up to ± 25 volts, compared to the 0 to 10 volts on the SLogic. It's also worth mentioning that SAILI's newer lineup has moved even further in that direction. Their new Logic MSO combines a logic analyzer and an oscilloscope in a single device. The entry-level model costs around $1,000 and offers a whopping 1 GHz digital sample rate. I'd love to get my hands on one of those at some point. The SLogic clearly wins on the raw digital sample rate. 800 versus 500 megasamples per second is a meaningful difference on paper and probably one of the most important specs. I will say though, I don't have the equipment to push neither of those devices to their absolute limits, and I can't verify that those numbers are actually correct. So for now, I'm evaluating the experience and kind of trusting that both manufacturers are being honest with their specs. From a usability standpoint, I personally prefer the Salier software. Logic feels more refined, especially when it comes to protocol decoding, exporting data, and building custom analyzers. PulseView and SIGROC absolutely get their job done as well. It might just be me being a bit picky. At the end of the day, if you need a solid and capable logic analyzer that doesn't kill the budget, the SLogic 16U3 is an absolute recommendation. Alright, that's it for now. I had a lot of fun playing with those devices. Thanks a lot for watching, and I'll see you next time.